The question that I got interested in was, is there any way to learn behaviors in a physics simulator where you actually have access to hundreds of millions of labeled examples, but then somehow make that work when the robot is put out into the real world?
You're listening to Gradient Descent, a show where we learn about making machine learning models work in the real world. I'm your host, Lucas Bewald. Josh is a researcher and an entrepreneur and a teacher. His work at OpenAI was on sim to real, creating virtual environments to create training data for robotics. He also teaches my favorite maybe class on machine learning called Full Stack Deep Learning. And if you haven't taken that class, you absolutely should. Previously, he did his PhD in computer science at Berkeley under Pieter Abbeel. I'm super excited to talk to him. You know, I think for a lot of people listening to this, just like knowing our demographics, I think a lot of people would probably be most interested kind of like learning about machine learning, and they might even know you from, some of the classes that you teach, which I think, in my opinion, are some of the best classes out there. I have to say, I've actually learned a lot from watching you teach. And I'm kind of curious, like, how did you even kind of get the idea of teaching a class? Like, how did that come up?
This sort of all started to happen around 2 years ago. I was working at OpenAI at the time, and OpenAI was kind of going through an interesting transition, I would say, where when I first joined, it was really felt like a very traditional academic lab. Like it felt like the lab that I was at Berkeley, except, more resources. At some point they figured out that there was a type of work that they were really uniquely suited to do, that a typical academic lab is not well suited to do, which is these sort of larger projects that involve, instead of just a couple of researchers working together, maybe a team of 12 or 15 folks, mix of engineers and researchers with bigger budgets, more ambitious goals, and really trying to push out these projects that would sort of clearly mark a move forward in the state of the field. So while this was happening, a big part of that change was we needed to figure out how we are going to professionalize our process of building machine learning models, right? And so on the robotics team, which I was working on at the time, we were figuring out stuff like, how do we write good tests for our machine learning code, right? So that you don't lose the ability to train a model that you were able to train a couple of months ago, which happened to us multiple times. And how do you actually manage a team that has both folks that are doing speculative research stuff that may not be able to really measure their progress in any given week, and also people who are doing very traditional engineering work that is where you can easily say this is the goal for this week and have we met that goal, right? And so we were trying to sort out all these things, and around that time I was talking to my PhD advisor at Berkeley, Pieter Abbeel, and a friend of ours, Sergey Karyev, who was running at the time a sort of machine learning for education company called Gradescope. And we're kind of just swapping notes on how we were approaching these things and how Peter had seen other companies approach these, and how Sergey had approached some of this stuff at Gradescope. And we realized that there was this whole emerging engineering discipline, I would call it, around you can go online and learn the math and the algorithms behind machine learning, right? You can learn what a neural network is. You can even really learn how to use TensorFlow, and how to code this stuff up in an effective way. But at the time, there was very little on everything else that you need in order to actually make this stuff work in the real world, right? So not only the things I described, but also how do you troubleshoot models? How do you choose projects? How do you manage teams? How do you deploy things into production? How do you monitor them once they're in production? And so we realized that there's everyone that we knew of was sort of reinventing the wheel on all these practices, and the number of people that are actually good at this is very small, and they happen to be trapped in a small handful of large technology companies in the Bay Area, let's say. And so we just thought it'd be really good for the field if we wrote down everything that we knew about this stuff and everything that our friends knew about it. And so that was kind of the genesis of the full stack deep learning class.
But I guess what's amazing, well, I never really thought about it this way, but I feel like I've spent my career, and I'm a little older than you, kind of like studying, making machine learning models work in the real world. But like watching your class, I'm like learning a ton, and I'm seeing you as like the expert. How did you get like up to speed on this stuff so fast? Was it just through the experience at OpenAI, or because your classes are amazingly deep?
Yeah, it's a good question. I mean, I think I was kind of at OpenAI at the most interesting point for this, right? Because we were sort of figuring this stuff out from first principles, and so there were tons of conversations around like, okay, like what tests should we have for machine learning models, right? And it was a really brilliant group of people there who like to take a problem and break it apart and look at it from the ground up. And so I think was able to like look at things from all the way down to the first principles level through that. And then I think it was really just about like trying to talk to a lot of the folks that are working in the field and see how they approach some of these things as well. Like a lot of what we the content that we put together in that class came from like 30 or 40 interviews that we did with practitioners and just trying to understand. We had a good sense of like what are the hard things and what questions do you need to ask if you're putting together a machine learning, like a applied machine learning team. And so just getting kind of a range of answers on those was also really helpful.
You have kind of a maybe a unique background in having been like a McKinsey consultant
Yeah.
for a number of years. Do you think that informed you at all? Like, do you think about how that might affect the way you approach this stuff?
I think like one of the things I learned from McKinsey was how to approach like sort of really abstract problems, like, what should our company do? Or, what should our org structure look like, right? And how to create so like these problems where it's like, okay, where do I even start in thinking about this problem? And I think, the question of like how to make machine learning work in the real world has this flavor. And then figuring out how to like break that down into parts and like structure your thinking around it is definitely like one of the sort of essential things that you have to do as a management consultant. And so I think that, that definitely informed the way that I looked at this problem.
So is there like a piece of your curriculum that you feel particularly proud of?
Yeah, I think the thing that I sort of put the most like emotional energy into is the troubleshooting guide.
Oh man, that's actually my favorite part too.
Yeah, because that was like that was the piece where I just felt like I was writing it for myself a few years ago more than anything else, right? Because
Totally.
I was just trying to like answer I was like, my perspective when I was writing that was like, okay, how could I have saved myself like months of time if I'd gone and started over in this field? So
Well, so I have to say, I got a chance to, to work for you briefly for, maybe a month or two.
yeah,
And I think like my big takeaway from you that I always like kind of hear in my head is you're like, you should always slow down and change one thing at a time. And I mean, I feel like that actually applies to more than, machine learning, honestly. But boy, does it apply to machine learning. Like, oh my God.
yeah, it's so essential in machine learning, right? Because it's like fundamentally, I think the thing that makes machine learning so hard is that like, when you're writing software, like when you're writing code, we have this like pretty mature ecosystem where like if you make a mistake, then usually the system that you're building or that you're interacting with will tell you, first of all, will tell you that you made a mistake, and second of all, it might even give you like a hint as to where that mistake is. But the insane thing about like actually trying to make progress on machine learning projects is that most of the time when you have a bug, the only thing that happens is that the performance of your model like doesn't get better as quickly as it should, right? And so there's no way of knowing that you actually made a mistake a lot of the time, unless you happen to have like really strong intuition about how like what your learning curve should look like, right? And so I feel like that's why it's so essential to move slowly when you're building new machine learning models.
Although it's kind of funny because I wonder if like programming, like web applications is the outlier here. Because I think about like, just trying to make an advertising campaign work well, or like trying to get my old motorcycle running again. And it's like, it's always better to change one thing because it's so hard to tell like what happened otherwise. But I guess maybe we have just better telemetry or APIs with, programming Python or JavaScript. I don't know.
I feel like that's right. I mean, I don't know. I mean, I wouldn't consider myself like a world-class web developer, but when I've done web dev stuff, it's also been helpful to still just change one thing at a time. I just feel like,
yeah, maybe it's just good advice for all situations.
Yeah, it might be. Anytime you're building anything, I feel like as you get better at something, you can like increase the the increment of what you can change at a time, right? Like if I'm training like a image classifier or something, right? Like I can pretty much just start with a like more like a newer architecture, like a ResNet or something like that, just because I've done that enough times that I kind of know what I can expect the result will look like if it works, and what common things that go wrong are. And so I feel like I can skip a couple of steps, but when I'm writing Kubernetes code, right, like something I'm very much not good at, I have to still move very, very slowly.
Would you be down to kind of walk me through your troubleshooting steps and how you think about them? I bet people will be interested.
Yeah. The core concept is what we've been talking about, right? Which is to start simple and then layer on complexity one step at a time, right? And so the first question you might have is, what does it mean to start simple, right? Mm-hmm. I think that like one of the things I've noticed with people that are getting into the field is that there's a tendency to there's all this excitement around like neural network architectures and the latest and greatest state of the art model on ImageNet. And so I think people like tend to overthink the question of architecture selection and and selection of all the other pieces around that, right? Like what optimizer you choose and things like that. But in reality, I think when you're starting out on a new project, the goal is to just choose a reasonable default and start there, even if it's not state of the art. And then like once you've convinced yourself that everything around that is working, right? So your data loading code and your training code and all of that stuff, then you can like gradually move closer to a state of the art architecture.
How do you convince yourself that this stuff is all working?
Yeah, it's a hard question. I think that like there's some tricks that you can use, right? So the first thing that I recommend people do when you're training a like let's say like a new neural net for the first time is just make sure that you can first of all just get the thing to run, right?
Like literally just like output something.
Just output anything, right? Which is not always like as easy as it should be. But like let's say that you've done that. Then the next thing that I think usually you want to do is try to like overfit a really small amount of data, right? So like a single batch of data. And it seems really simple, and a lot of people skip over that step because of that. And 80% of the time it's not really necessary, but 20% of the time you can catch some like pretty nasty bugs early on.
So like I often recommend this, citing you, and I think I'm sure that this is not obvious to most people. Like, why do you want to overfit a small amount of data?
So like any reasonable like model architecture and optimizer and training loop and data type, you should be able to get like your loss down to zero on a single batch of data, right? You have enough parameters that the neural net should be able to just memorize the data. And so, basically like if it can't do that, then you know that you must have like a pretty bad bug in one of those things.
Like what kind of bug, for example?
Like you flip the sign on your loss function, right? And
Right.
And like your loss actually goes up rather than going down. Or like another one that I see all the time is in like a lot of these neural network libraries, you have to input the inputs to the loss function is maybe it's like the logits, right? So it's like something unnormalized, but maybe you took the softmax of that first. And so it's like it's things like that, right? Where it's it's just like you wrote the code the wrong way. And this is just like a quick sense check for figuring out like, is the code that you're running reasonable?
Okay. And so then, sorry, I cut you off. Then what do you do when you can overfit one tiny subset of your data?
Yeah. So when you can overfit a tiny subset of your data, then like I would say like one way to think about the process of making your neural net better and better over time is there's like an outer loop and then there's an inner loop, right? And so the outer loop is um, you know, is basically like you're generally trying to do one of two things. You're either trying to like reduce the amount of underfitting that your neural net has, or reduce the amount of overfitting that the neural net has. Um, and so, and like there's a lot of strategies for doing both of those things, but the best strategy for reducing underfitting is to make your model bigger, and for reducing overfitting is to add more data. And so if you think about what we just did with overfitting a single batch of data, um, or with like driving loss down to zero on a single batch of data, we're basically saying like, let's take the smallest possible data set and let's overfit it, right? And so now the next like question in your decision tree should be like, all right, now we know that we're overfitting because we can drive loss down to zero. So the next thing that we should do is reduce overfitting, and the simplest way to do that is to add data. But you want to do this gradually, right? So typically what I would do next is I would move from a single batch of data to like a smaller or more simplified version of the data set that I was working with. So maybe it's like, I don't know, you just take, maybe you have 1 million images, but you just take 1,000 or 10,000 of them to start out with. Maybe you make a synthetic sort of toy version of the problem that you're working with. If you're doing reinforcement learning, maybe you work with like one of the standard sort of simple benchmark problems like cart pull or something like that. And so it's like you just make the problem like one step more difficult than a single batch of data.
I see. So you add one sort of piece of complexity?
Yeah, that's the way I think about it. Is it's like
and why wouldn't you just add all the data that you have? Because like your conclusions, I imagine they could change at different scales of data, for example.
Yeah, definitely. I think there's two core reasons, right? So one is a lot of times, I guess like maybe the simplest one to explain is that it just reduces your iteration time, right? So if you're working with a smaller data set or a simpler data set, then typically your model will train faster, it'll be cheaper, and so you can just try out more things more quickly, which is super key. But I think like the deeper and more interesting reason is that if you like a lot of times in machine learning, you have like some degree of confidence that this model should actually be able to solve the task that you're working on. But a lot of times you don't actually know that for a fact, right?
Mm-hmm.
Like maybe you're doing image classification, but you're not doing it on ImageNet. You're doing it on some other data set. Like maybe you're classifying like whether something is whether a person is wearing a hat in an image or not. And so it's like intuitively you feel like it should be possible to solve this with a neural net, but you don't actually know that for sure. And so you want to try to isolate the sources of error in your problem, right? And so if one of the possible sources of error is that like this data set is just too hard, then it makes sense to start with a version of the data set that you know that your model should be able to do well on. And so smaller data sets, less complex data sets allow you to do that.
But wouldn't a smaller data set make the problem harder?
In what sense?
Like if, say I'm trying to classify if someone has a hat on or not, if I have less training data, I would expect my accuracy to be lower, right?
Yeah, that's definitely true. I think that like, so I guess this comes back to like the overall process that we're trying to follow, right? So it's like, I think of it as iterating between, eliminating underfitting and eliminating overfitting. And so if you're in a situation where your model is like doing perfectly well on your training set, then it makes sense to increase the complexity of your training set. If you're in a situation where your model can't do well on the training set, right, then you need to figure out like, is it that my training data is too hard? Is it that I need a bigger model? Is it that I need a different architecture? Is it that I need a different optimizer, different hyperparameters, right? And so like working with a data set where that's easier to get to that point of your model overfitting, just like reduces the number of things that could be wrong with your model.
Interesting. Are there more steps to this?
I mean, that's the high level flow, right? Is like solve your problem, make it harder. Solve your problem, make it harder. And then there's details about how to make each of those things work well, right? Like what are the steps you should actually try, when you're underfitting and you need to like make your model more expressive. Um, and yeah, but I think that like that's sort of like the overall picture.
We'll have to put a link to this in the so people can find it. Do you plan to teach more of these classes?
I think so. Yeah. We don't have concrete plans to do another one. I mean, it's not a great time for in-person classes.
Maybe a virtual one would be.
Yeah, maybe a virtual one. That could be fun.
Hi, we'd love to take a moment to tell you guys about Weights and Biases. Weights and Biases is a tool that helps you track and visualize every detail of your machine learning models. We help you debug your machine learning models in real time, collaborate easily, and advance the state of the art in machine learning. You can integrate weights and biases into your models with just a few lines of code. With hyperparameter sweeps, you can find the best set of hyperparameters for your models automatically. You can also track and compare how many GPU resources your models are using. With one line of code, you can visualize model predictions in form of images, videos, audio, plotly charts, molecular data, segmentation maps, and 3D point clouds. You can save everything you need to reproduce your models days, weeks, or even months after training. Finally, with reports, you can make your models come alive. Reports are like blog posts in which your readers can interact with your model metrics and predictions. Reports serve as a centralized repository of metrics, predictions, hyperparameters tried, and accompanying nodes. All of this together gives you a bird's eye view of your machine learning workflow. You can use reports to share your model insights, keep your team on the same page, and collaborate effectively remotely. I'll leave a link in the show notes below to help you get started. And now, let's get back to the episode.
Do you have any advice, I suppose, to folks wanting to get into machine learning? I'm sure a lot of you probably watch a lot of students kind of learn it or not learn it. Do they have any sense of like what's required?
Some people look at something like machine learning and they say like, okay, this is a really deep field, right? And there's a lot to learn here. There's a lot of complexity, like so many papers, thousands of papers coming out every month. And so I want to just, I want to just drink from the fire hose and try to just learn as much as possible. And then on the other extreme, there's folks that say like, look, this field is so complex that I want to just like pick a problem and solve that problem. And I think there's failure modes on both ends of that. I think I work with people who see the complexity of the field and react to that by just like learning more and more and more, but never actually like really getting their hands dirty and figuring out how to make this stuff work in for the problems that they care about. I think that typically doesn't work. And then I've seen like probably just as many people who don't want to deal with the complexity, like don't want to learn the math, don't want to understand how a ConvNet works. And I think that also limits your ability to like make progress in the field, because ultimately it's closer to a science than an engineering discipline right now, I would say. And so I think you need to like balance spending time on actually doing stuff and like following tutorials and making things work, and then also like going back and backfilling, like, okay, now I've trained ConvNet on this image classification task. Like I know how to write the TensorFlow code. Now let me actually go back and understand how ConvNet works.
The folks that you've seen that have been successful, like really kind of learned this stuff and had like started to get good careers as successful people. Do you think they spend more time on the theory on average, or more time on the practical hands-on stuff, or is there some other third thing that they're doing more of that makes them successful?
I would say more time on the practical hands-on stuff. One of the interesting things about machine learning is that although there's a ton of complexity in the field, there's a relatively small number of like sort of core ideas that you actually need to really deeply understand in order to be an expert in the field, right? Like understanding attention in neural nets is really important. understanding how backpropagation works is really important. But like understanding, all of the different state of the art architectures for like, doing object detection, not really very important unless you happen to be like working full time on that problem. Mm-hmm. And so I would say that like the people that I know that have successfully learned the field have tried to, I would say that they've spent more time with a smaller number of ideas. And, rather than like trying to read, 5 new papers every day, they've like went out and talked to people and figured out what the 5 most important papers are. And then have spent, weeks with each of those to like really deeply understand them. But then I've probably spent the balance of their time like actually trying things and implementing things.
Mm-hmm. That makes sense. When you look at the papers that you've written, do you have a favorite?
I think my favorite is actually the first one that I was like the lead author on, which was the domain randomization paper.
Oh, cool. Sim to real.
Sim to real, yeah.
Can you tell me the real process of kind of like, thinking of that idea and then like trying it and how that all happened? Well, I guess first describe the idea, because it seems like one, like the rare paper you can really kind of succinctly describe it, right?
Yeah. When I was starting to work in this field, right, so like the intersection of deep learning and robotics, back in 2015, there was a lot of excitement around reinforcement learning being applied to robotics, right? So like reinforcement learning, you have an agent that interacts with an environment. It takes some observations of the environment, decides what action to take, and then gets a signal back from the environment, which is a reward that tells it like, did I do a good job or a bad job? And then over time, it iteratively learns how to interact with that environment and improve its performance on whatever task it's supposed to be doing, right? And so it's like a very natural abstraction for robotics. Back in 2015, like deep reinforcement learning was like starting to have a bit of a renaissance, right? It was, starting to work really well on Atari games. I think that was, 2015 or 2016 was when DeepMind beat the best human players in Go, right? And so people were looking at this and saying like, wow, this could be like the like most important technology to come to robotics in a really long time. And so I was, early on in my PhD at that point, and like the exciting thing to work on was like coming up with what's the best new, reinforcement learning algorithm. Like how can we improve our performance on all these tasks? But I was like very new to the field, and I didn't feel like I had a good, I felt like it would not be very smart for me to try to compete with people who like have been studying this stuff for years and had like a lot of insights into what made those algorithms work, right? And so what I tried to do was think about like, okay, what are like the enabling pieces that we need in order to actually, for this story to come true, right? For the story that like deep reinforcement learning is going to have a big impact on robotics. And for me, the big, like the piece that was kind of missing for that story was that, deep reinforcement learning is very powerful, but it's very data inefficient. Like all of these sort of state-of-the-art results that you see happen in environments where you can sort of simulate everything that's happening, because it takes, hundreds of millions or more of interactions with the environment to actually get to the point where you have human level behavior. And so like for me, kind of looking into this field from the outside, that was sort of the big question mark, right? Is there any way for us to get around this data inefficiency problem for robots, right? Because like going out and collecting 100 million, examples of a robot interacting with an environment is not very cost effective, let's say.
Google did this, right? With an arm farm?
Mm-hmm. So it's definitely possible, but it's, do you really want to have like dozens of robot arms running 24/7 for weeks every time you want to learn a new behavior?
Sure, yeah.
And so coming back to this paper, right? Like the question that I got interested in was, is there any way to learn behaviors in a physics simulator, right? Where you actually have access to hundreds of millions of labeled examples, but then somehow make that work when the robot is put out into the real world. I was kind of working on this, back when I was an intern at OpenAI, and we had like a really concrete problem that we were trying to solve, which is, we were trying to set up a robot to like make a stack of blocks. So to like pick up blocks from a table and then, stack them on top of each other. And like the policy, like the robot behavior was trained assuming that you actually know where the blocks are in the real world. And so then we needed to like go back and backfill, like how do we actually find out? How do we estimate the position of each of these blocks in the real world? It's something that seems like a really easy problem, but actually, when you think about how do you make this really work, it's more complicated than you'd expect.
Honestly, it's so counterintuitive. I think even for me and probably for most people, right, that's hard. Just it's amazing that that's hard.
Yeah, and I think it's not like the hardest research problem in the world, but it's like when you actually sit down and try to go and make it work really well, it's very tricky.
Sure.
And so we were playing around with these different like tag Aruco tags and like methods like that where you understand the intrinsics of the camera, and then it reads this tag off of an object, and then it can infer the position of the object given the position of the camera. And we just found those things to be like really fragile and honestly not really that accurate. Without investing in like expensive setup and expensive camera equipment and stuff like that. And so the question was like, we were mostly deep learning folks, right? And so the obvious question is like, why don't you just train a neural net to do this? Just train a neural net to take an image of a table and then say like, okay, here are the position of all of the cubes on the table. But the problem is that like, where do you get the labels for the data set that you collect, right? You almost need to solve the problem. You almost need to know where the cubes are in order to actually get the labeled data set that you use to train the neural net, right? So it's a bit of a chicken and egg problem. And so this is kind of the starting point for me working on this sim to real problem is like, okay, this feels like the simplest possible example of a problem where maybe synthetic data, data from a physics simulator would actually help.
So then describe what you did.
So the core idea is that, if you just take data from a simulator kind of naively and train a model on it, the problem is that, there's quirks of your simulator, right? Your simulator doesn't perfectly match the real world. And so the neural net will overfit to any difference between the data in the simulator and the data in the real world. So, if you didn't perfectly model the lighting, you didn't perfectly model the color of the cube, the neural net won't transfer. And so the idea that we had was like, what if you, instead of just taking like a single best physics simulator, what if you massively randomize every aspect of the simulator that's not, critically important to solving the task, right? So you randomize the colors of all of the objects, you randomize their positions, you randomize the position of the camera, you randomize the background, and it produces images that are like crazy and like unrealistic looking, right? So they look like they look like scenes from like an anime disco or something. But what happens is that actually the neural net, in learning how to estimate the position of the cube in all of these different like massively different worlds, is forced to not rely on the parts of the simulator that are not essential for solving the task, right? So if the color of the cube changes in every single data point, then the neural net can't create a feature that depends on the color of the cube to solve the task, because that's just an unreliable piece of information. And so then when you do this, it turns out that you can train neural nets on entirely simulated data, so no real world data at all, that actually work when they're deployed in the real world.
Because you just kind of like cycle through lots of colors and shadows and other
Yeah, exactly. It's you basically show the neural net like every color and every shadow that it could even possibly see, and so then it in order to solve the task, it needs to learn like, okay, that's colors and shadows are not important, right? What's important is like the position of this cube looking thing on the table. And so it's not overfitting to like all the details that are unimportant. And it's actually, and so then, the details that it is looking at are the ones hopefully that will transfer over when it's deployed in the real world.
And so how far can this generalize? Has this been applied to more than stacking blocks now?
Yeah. It's been applied to like a pretty wide range of sort of computer vision and robotics tasks at this point. I think, been applied to my favorite like random application was there's a paper about using domain randomization to train a robot to pick fish out of a barrel.
Really?
Yeah.
Wow.
Which is actually a really hard task because fish are very shiny and slippery, right? And in general, like most like object detection methods and like computer vision stuff has trouble with like objects that have a lot of reflections and things like that. So that was my favorite like random application. But it's been applied to folding cloth. It's been applied to pretty wide range of computer vision problems. And I think like maybe the furthest this idea has been pushed was at OpenAI when they use this technique to have a robot hand that solves a Rubik's Cube.
Can you say a little bit about why that was such an impressive task? Or I guess there was some controversy, right? About like, is this sort of like a stunt or is this like a real deep task? I guess where do you land on that?
So maybe the different sides of this issue would be like, on one hand, I think if you look at the types of things that, the types of tasks that people have been able to solve with robots over the years, this task of this sort, right, like using a high-dimensional dexterous robot to manipulate a complicated object, are very sort of few and far between in the robotics world. And it's kind of generally seen as like, high-dimensional, contact-rich, dexterous manipulation as being like sort of one of the grand challenges of robotics. And so I think one point of view on this is that even just something at like a proof of concept level to show that it's like possible to even do this once is a big step for the field because there's very few examples of there are some, but there's very few examples of projects that have pushed robotic manipulation as far as being able to solve a Rubik's Cube. I think the other perspective would just be that like if you look at the details in the paper, the algorithm like actually worked something like 20% of the time, and so you might argue that like and it was a pretty big effort to get to actually make it work for the first time, right? So pretty big team working on it for a long time, and so you might argue that like obviously if you put 10 or 12 really brilliant people and have them work on one tiny like sliver of a problem for a long time, then obviously they'll be able to make it work once. I would say that
that's not obvious to me. I don't know.
I'm trying to play devil's advocate here. Like my bias is that it's an important result in robotics, and I think that but I think like the perspective that you have to have when you look at this is that it is very much a research result, right? Like I think a mistake that people make when looking at results like this, and I think this is true in AI in general, is that like you look at humans or like computers being better than humans at any task, and you say like, okay, this means that like robots are going to take this job in 2 years, and it's like not like if you look at the details of how hard it was to actually make this work once, 20% of the time, it's like there's a lot more research that'll need to happen in order for this to become a thing that robots can do reliably. But I do think there's a lot of value in the proof of concept, just to show that like this is a set of techniques that this team was able to push far enough to do this task that is like objectively really difficult for robots to do. And then over time the field will backfill like how to actually do that in a more efficient way.
I guess I didn't realize it only worked 20% of the time. This is like 20% success rate, meaning completely manipulated the cube to be back in the like correct state. Is that right?
Yeah, I think the fine print is for the like hardest variant of the problem, which is like the cube randomized as much as it can be. The robot was only able to get it back to fully solved 20% of the time. I think on average it did it more than that, and I think also, like maybe one of the other details people took issue with was the fact that there was the machine learning algorithm itself did not didn't say like the sequence of actions that you need to solve the cube, right? It didn't like it wasn't like a neural net was saying turn this face and then turn this face and then turn this face. There was like hard-coded solver that was saying the sequence of actions that you take. And then the neural net was just saying like, okay, here's how you move your fingers in order to achieve this action.
So the point was the manipulation. So people are mad because it was like a fun demonstration. Maybe.
I think people often take issue with the way that OpenAI communicates results like this, more so than the results themselves.
Because it seems like they're generating attention. Is that right?
I think so. Yeah. I think there's a bit of a tension in the field right now of between kind of people who maybe have more traditional academic roots and who think that it's like the quality of the scholarship that's important, and like whether it's truly novel, whether the results are like really understandable and reproducible, on one hand, and then on the other hand, folks who typically are more of like the more industrial research lab type places where I think the viewpoint is more like our goal is to like push the state of the art of the field forward. And if we have to do that in a way that's like not totally, not 100% reproducible, just because like maybe the experiment was too expensive, and that's okay because we're moving the goalposts forward of like the types of things that AI is able to do. Yeah, and I think there's like kind of a fundamental tension there.
That makes sense. So I guess you've left OpenAI. So what are you working on now, Josh?
Yeah, no, it's a good question. One of the things that I learned through full stack deep learning is, I guess maybe one of the beliefs that I have about this field is that like I think there's this narrative in the machine learning world that like AI is going to be part of everything, and like it's just going to be like software where it's like just sort of happening in the background as part of like every little thing that we do. And it's going to enable all these like amazing new applications like self-driving cars. But in general, it's just going to be like there in the background, making the world like 10 or 15% more efficient or more. I don't know. But we're not there yet. And so like one of the kind of core questions for me over the last, 6 months or so since I left OpenAI has been, why is that? Right? Like what's blocking us from, having like just a little bit of machine learning that's just making sort of every piece of software that we interact with smarter. And that's sort of the root, like the fundamental question that I'm trying to answer with this company.
It's so interesting. We actually always have been ending this podcast with two questions, and that question has been one of them. I mean, you've clearly like been spending a lot of time thinking about it. Like, what's some of your conclusions? Like, if you had to pick like one thing, what would that be?
I mean, I think this comes back to our conversation about the robot hand, right? Like, I think the field has gotten really good at doing really impressive things once, but then one of the dirty secrets of machine learning is that turning something that works once, or like I don't know, is 90% accurate on like one data set, turning that into like a reliable production system that you can that is auditable and is maintainable and it's understandable, and you can actually like start to run your business on. That's really hard, right? And so I think like figuring out how to answer that question is sort of the big question that the field needs to answer right now.
Yeah, I guess it's kind of counterintuitive to see a computer do something 20% of the time. Like that feels like a really like I feel like most times if I see a computer do something that I know, like, okay, it's going to do that 100% of the time.
Yeah, no, definitely. Yeah, for sure. I mean, I think it's like, maybe one of the other things that I've seen through full stack deep learning and through like some of the other folks that I've talked to who are like trying to implement machine learning in their companies is that oftentimes like one of the hardest things to do is just like figure out how to get the executives in your company, let's say, like the folks that are making the decisions but are not deep in the technology, to actually understand what can we really do with this stuff, right? And it's like, yeah, I think that's one of the things that's really hard about machine learning is that like it's it's not always clear. There's not always a clear connection between like what you read about what it can do and what it can actually do. And like communicating that, I think, is like another big challenge for the field.
Do you have any suggestions there? I mean, almost everybody we've talked to has brought that up.
Someone needs to make a really good class that's like AI for for everyone. Andrew Ng has a class. I haven't gone through it. Maybe that's the answer. But I think like you can build intuition for this stuff, but I think that doesn't come from reading like the New York Times headlines. It comes from actually sitting down and looking at examples of things that work and things that don't work. So I don't have a good suggestion, but I do think that there's a big opportunity to make that.
It's funny. I've heard that that like IBM Watson in its heyday would like fly executives to like a lab and just like kind of blow their minds and get them like hyped out of their minds at the potential of AI. It's just like really awesome demos. And I've always had this fantasy of like doing like the opposite of that, do like an hour with like execs and make it like really kind of hard and boring and like, let them like fight with the the AI for a while. Like, even just try to like, tune some hyper parameters to like actually get the thing working. I think would be a fun, I think it may be an informative experience, for a lot of people. Maybe help the execs understand why their, ML teams aren't producing results as fast as they were hoping.
I think that also like one thing that would help a lot is I think the methodology, this is like sort of what we tried to do with full stack deep learning, but maybe didn't really get all the way there. But I think that like the methodology of successfully building machine learning systems is still pretty immature, right? Like it shares a lot with software engineering, but is really a different field. I think that like, if there were like an agile equivalent for building machine learning systems, I think that would also go a long way. Because it's really just like the block and tackle of like, how do you actually make this happen? So it doesn't feel as much like magic and like, what are those crazy data scientists doing over in their corner over there? And it feels a little bit more like, okay, I understand that, this is the set of meetings that the team is having every week, and this is how they're measuring their progress. I think like something more operational like that could also go a long way.
Seems like you'd be the right guy to figure that out.
I don't know, maybe.
All right, here's the other question we always end with, which I'm really curious to know what you'll say. So just off the top of your head, what's like a sort of underappreciated topic in machine learning that you think people should talk about more? I mean, given all the hype on so many of the topics, what's a piece that people don't pay enough attention to?
I think that people don't pay enough attention to quality of their training data.
Oh man. I agree, Josh.
But it's so important.
So important. Nice. All right. Well, that was really fun. Thanks for taking the time to chat.
Yeah, thanks for having me on.